Thank you. I should start by saying which is the aim of my presentation. In 1975, Lipscomb introduced a kind of important space for the topological dimension theory. And recently, with my colleague Alexandru Mihail, we introduced a generalization of this space. We denote it by JGA, and we call it the graph Lipscomb space associated with a graph G on a set A. And what we are going to do today is to see when this space is connected, and we want to have a characterization in terms of the graph G. And first of all, I'm going to introduce this space. Then we are going to have a topological copy of the graph Lipscomb space inside a space little L2. And finally, this copy will be presented as a fractal set. And this will give us the opportunity to see when it is connected. So let me start by introducing the graph Lipscomb space. And first of all, I should say some words about the bare space. The idea is the following: we have a set A, and for each natural number n, we are looking at the topological space an tau n. An all the time is A, and tau n is the family of all subsets of A. And then we take the product of this countable family of topological spaces, and what we get is the bare space, which is denoted by n of A. So this means that from the algebraic point of view, n of A is nothing else but the set of all sequences with elements from A. So this means that the generic element of n of A, which is denoted by omega, actually is an infinite word with letters from A, and will denote the letters by omega 1, omega 2, and so on. And such a point is called an endpoint if, starting with some position, all the letters are the same. So if we can find a k such that omega k is the same with omega k plus j for every j. All right. So n of A is a topological space, but actually the topology comes from a metric, which is denoted by rho here. The metric is described in the following way. The distance between omega and theta is 0 if omega equals theta, but otherwise is 1 over the minimum of those k such that omega k is different from theta k. So this means that the longer is the initial segment on which omega and theta coincide, the smaller is the distance between omega and theta. Also, it's good to note that this metric space is complete and it is compact if and only if A is finite. We are going to use this piece of information later. And now I want to say, what do I mean by a graph on a set A? So we have a non-empty set A, which is called the set of vertices. And then we have a set G, which is called the set of edges, such that all the elements of G are sets with two elements U and V in A, but we want to have inside of G also the sets consisting on one element U of A. So in particular here, if we take U equals V, we get this one. And then the pair consisting of A and G is a graph on A. Now I need another notion. What do I mean by two adjacent endpoints. So let us suppose that we have a graph G and we have two distinct endpoints, omega and theta. And if starting with some position, we can find two different elements, x and y, such that the set consisting of x and y is an element of G, such that omega looks like x, y, y, and so on, and theta is y, x, x, then we are going to say that omega and theta are adjacent endpoints with respect to the graph G. So in other words, omega and theta are adjacent endpoints if they have a switching tail, if I can switch x and y. And now we can define an equivalence relation on the bare space. Omega and theta are equivalent if they are equal or if they are adjacent endpoints with respect to the graph G. And the graph Lipscomb space G actually is the quotient space of the bare space through this equivalence relation. When G is maximal, so when we take G to be the set of all subsets with U and V in A, we get the space of Lipscomb, which is denoted by JFA. This is why we call our space the graph Lipscomb space. And I want to say some words about the importance of the Lipscomb space. In 1931, Noebeling proved the so-called classical embedding theorem for separable metric spaces. The result provides actually a subspace of 0, 1 to the power 2n plus 1, which is universal for n-dimensional separable metric spaces. But later on, Katetov and Morita introduced a theory of dimension theory for general metric spaces, which are not necessarily separable. But one problem that was unsolved until 1975 was the lack of a similar universal space for n-dimensional metric spaces which have weight greater than Aleph 0. And the problem was solved in 1975 by Lipscomb just by introducing this space JFA. And actually, Lipscomb proved that for a finite dimensional metric space, which has the weight greater than Aleph 0, we can embed it topologically in a finite product, in a finite product of GAs. So in other words, we can replace 0, 1 here by JFA. All right, so now we know what does it mean, the graph Lipscomb space. And the next step would be to have a topological copy of this space into the space little f L2 of A prime. Let me recall that if I have a set A with at least 2 elements, I will fix an element Z in A. By A prime, I mean A except Z, and we can look at L2 of A prime. This means that we have families of real numbers, and the index J is in A prime. Xj is not 0 for only countably many J's, and the sum Xj squared is convergent. And from now on, instead of writing Xj with J in A prime, we write just Xj. And we know that we can organize little L2 as a Hilbert space because we have a canonical addition, a canonical multiplication with scalars, and also we have a canonical scalar product. So L2 is a Hilbert space. I will denote the zero element by UZ, and by UJ, the family that has zero on all the positions except the position J. Okay, and now we want to produce the topological copy inside of little L2. The first step is to construct a function from the bare space into little L2. But in order to describe this function, let me explain this. We need this notation. So we have A prime, and B in A. And by C, A prime, B, I mean zero if A prime is not B. And otherwise, the constant will be 1/2 or 1/3 according to the case when AB, the set consisting of AB, is in G or not. All right, and now we can construct this function PG from the bare space into L2. The function is given in this way. So PG of the word omega is the family with the components alpha B of omega, where alpha B of omega is given here, is the sum over I from 1 to infinity of the product over J from 1 to I of C omega J, omega I, and B. So this means that we take one letter from here, omega I, and we want to see if this letter is B or not. If the letter is not B, then the constant is 0. So actually, we care about just the letters which are B. And for such a letter, omega I, we look on the letters in front of omega I. If the letter in front of omega I with omega I, which is B, is an element of G, on the product we put 1/2. Otherwise, we put 1/3. And in this way, we get the function PG, which is a continuous function. And let us denote the range of PG by omega AG. So omega AG is a subset of little L2. And therefore, on omega AG, we have a distance and we have a topology. Now, using this function SG, we can construct, having the function PG, we can construct the function SG from the graph Lipscomb space into omega AG, which sends the class of omega into PG of omega. And it turns out that this function is well defined, for sure. And moreover, which is very important, it is a homeomorphism. So from the topological point of view, the graph Lipscomb space and omega AG, they are the same. If I want to see when this one is connected, I should look at omega AG. Is a good move because here on omega AG, I have a distance. All right, the next step and the last one is to look at omega AG as the attractor of a possibly infinite iterated function system. So let me recall what is a possibly infinite iterated function system. Is just a pair consisting on a complete metric space, XD, and a family of contractions, Fi, from X to X. And we want to have these two properties. We want to have the supremum of the Lipschitz constant to be less than 1. And also, we want to have just one element x0 in X, such that the family Fi of x0 is bounded. And here I should point out that I, the set I, is finite or not. It doesn't matter. But when I is finite, we can see that these two conditions, alpha and beta, are satisfied. And actually, in this case, we have the classical concept of iterative function system, which is due to Hutchinson and Barsley. Also, I want to emphasize that this condition beta implies the following. If I take a bounded subset of X, then the union of the images of this set through the functions Fi is a bounded set. And if I have such a system, then we can look at the fractal operator associated with the system S, which is a function defined on the family of bounded and closed subsets of X with the value on the same family. The operator Fs acts in the classical way. So it sends B, a bounded and closed subset of X, into the closure of the union of the images. And for sure, this function is well defined because of the second condition. So we are sure that the union is a bounded subset of X, and then we take the closure. So Fs is well defined. And moreover, we can see that this operator Fs actually is a Banach contraction with respect to the Hausdorff-Pompeiu metric. And therefore, it is a Picard operator. In particular, it has a unique fixed point, which is denoted by A sub S. And the sets which are obtained in this way are called generalized Hutchinson-Barsley fractals. And for a metric space, for a complete metric space, XD, we will denote by GHB of X the set of all generalized Hutchinson-Barsley fractals inside X. Also, I want to emphasize that we can present the attractor AS as the limit of the iterated, okay, let me say it some other way. So if I start with a closed and bounded subset of X, and if I apply the fractal operator again and again, at the limit, I will get the set AS, which is the attractor. This is important from our point of view, and would be a good idea to see what happens when the set I is finite. In this case, it's clear that if I take a compact subset of X, and if I apply the fractal operator, I will get again a compact subset of X. This means that I can take a look at the function Fs tilde from the family of compact subsets of X into itself. Fs tilde of K is a union of Fi of K. So actually will be the same with Fs of K because I is finite. Okay, so in other words, I can restrict the fractal operator to the family of compact subsets of X. And we know from the classical theory of Hutchinson and Barsley that Fs tilde has a unique fixed point, As, which is a compact subset of X. So it is also bounded and closed. So this will be also the fixed point of Fs. All right, let us call the sets that are obtained in this way Hutchinson-Barsley fractals, and we denote for a given metric space X this set by HB of X. So this means that for sure we have HB of X is a subset of GHB of X. This is why we called the set from here generalized Hutchinson-Barsley fractals. And I also want to point out that this is a real generalization of the concept of Hutchinson and Barsley. Why? Because we can look at our old friend, bare space, and we can see that actually the bare space is the attractor of a possibly infinite iterated function system, which is described here. So the metric space is N of A with rho, and the family of contractions is given in this way. We have tie I from N of A into N of A. Tie I of omega is I omega, and it's not very difficult to see that N of A is the attractor of this system. So N of A is a generalized Hutchinson-Barsley fractal, but when the set A is infinite, then N of A is not compact. And therefore, it cannot be the attractor of an iterated function system with a finite number of functions. All right, so this means that this is a real generalization. And now let us come back to our problem. And we can consider the following possibly infinite iterated function system, which is denoted by SAG. The metric space is little L2 of A prime, and the family of contractions is given in this way. So Fi of the family Xj is 1/2 of Ui plus the familyCijj Xj. And here we have our first basic result, which says that the attractor of this system actually is omega Aj. So actually it is the topological copy of the graph Lipscomb space. In other words, the embedded version of the graph Lipscomb space is a generalized Hutchinson-Barsley fractal. And now here is the main result. It states that in the previous framework, the following three statements are the same. The first one is that the graph Lipscomb space is connected. The second one, omega Aj is connected. And the third one, the graph G is connected. When I say that the graph G is connected, I mean that for every X and Y in A, we can find a finite number of elements from A, X0, X1, up to Xn, such that the sets X0 consisting of X0, X1, X1, X2, and so on, all of them belong to G, and the first element is X, the last one is Y. So this means that we have here a characterization of the situation when the graph Lipscomb space is connected in terms of the graph G. For sure, one the same with two is obvious. If how many minutes do I have? 5 minutes. I can say some words about the proof of this result. First of all, about the implication, 3 implies 2. So here the big idea is the following. If I want to look at omega Ag, this is actually the attractor of the system. So this means that it is the limit of the sequence AN, which is given in this way. I start with an arbitrary A1, which is a bounded and closed subset of little L2, and then I apply the fractal operator. And the big idea is the following. We are able to choose A1 such that the sequence AN is increasing, so AN is inside AN plus 1 for every N, and such that all the sets AN are connected. Then the limit of AN is the closure of the union of AN, and therefore this set is connected, and omega AG will be connected. But here is not so easy to choose A1 with these two properties. And in order to say how to choose this A1, let me recall that if we have such a possibly infinite iterated function system for which I is finite, then we have a result, a classical result, which says that the attractor is connected if and only if the family of the images of the attractor through the functions fi is connected. Okay, by a connected family of subsets of a metric space, I mean the classical definition. And using this theorem, we can see that the attractor of such a system, which consists just on two contractions, Fi and Fj, with I and j, such that the set consisting of I and j is in G, the attractor is connected. And then the next step would be to see that the family of SSIJ with IJ in G is connected. And then the union of them is connected. And finally, we can take A1 to be the closure of this union. For the implication 1 implies 3, here is not big deal. We can suppose that G is not connected. Then we can find a partition of A given by the sets S and T, such that if I have an element of S and one in T, the set consisting of those two elements is not in G. And then we will produce two open and closed subsets of N of A, S prime and T prime. So in S prime, we have all the words starting with something from S. In T prime, all the words starting with something from T. And also we can see that omega is equivalent with theta if and only if both of them are in S prime or both of them are in T prime. And this will give us the contradiction that the graph Lipscomb space is not connected. And finally, I should say that when the set I is finite, we can say more. The following three statements are the same. The graph G is connected. The Lipscomb graph space is connected and locally connected. And the third one, this space is arcwise connected. And thank you very much for your attention. You mean the other way around? Maybe.